video, we're going to take a look at confidence intervals. And confidence intervals are what we're going to use to take sample data to make predictions about populations. So to start, let's recall the model for the distribution of sample proportions. That is our sample proportion p hats. So sample proportions. And they are approximately normal with a mean of p being the population proportion and a standard deviation of the square root of pq over n, provided we meet the following assumptions. And these are the same three assumptions that we've had for the last few sections. Random, and we check the problem statement for that. And we also need to make sure we have independence, and that's going to be typically almost all the time for the stuff we're doing here with our samples. We're drawing from a population. So we're checking for pseudo independence, or that n is less than 10% of the population. And we're checking that we have a large enough sample size to overcome any non-normal behavior. And that's checked by calculating NP and NQ and verifying that they're both greater than 10. Greater than 10, or at least 10 works as well. So for example, we are told that a coin is fair. With 68% certainty, what proportion of the time should we get heads in 100 flips? What about if we are looking for 95% certainty? With what proportion should we get heads in 100 flips? So in this case, we are looking at our normal distribution first and foremost. So if we have our expected value of p hat, that's just going to be 0.5, right? We expect 50-50 for heads to tails. Standard deviation of p hat, we can calculate that. And that'll be our 0.5 for p, 0.5 for q, and divided by our number of flips, which is 100. And that gives us 0.05. So we expect most of the time that our samples of 100 flips will have about 50% heads, give or take about 5%. All right. And so in a picture, what we're looking at then is we're going to see for 95% certainty, remember, we're going to have our center at 0.5. And if we go out 1, 2 standard deviations, and that's going down by 0.05, so 0.45, 0.40, 0.55, 0.60. This is proportion of heads in n equals 100 flips. Then if we're going to know that these are all of our sample proportions, well, with 68 or 95% certainty, what proportion of the time should we get heads? Well, that's talking exactly about the bounds here that we have, right? Because by our 68, 95, 99.7 rule, we expect within one standard deviation here that we'll get 68% of proportions. Will be between the 0.45 and 0.55, and then we would expect within 2 standard deviations, we would have 95% of proportions there. Proportions, there we go. So we expect with 95% certainty that we will get between, right, within 2 standard deviations for that, so between 0.40 and 0.60 heads. And then we expect with 68% certainty that we will, there we go, get between 0.45 and 0.55 heads. And we'll kind of put that on the sidebar because that's the proportion of heads that we're expecting. So we're expecting to get between 45 and 55% with 68% certainty, and between 40 and 60% heads with 95% certainty. Okay, because that's just based off of the 68, 95, 99.7 rule. Well, that's all well and good. That should not make us feel uncomfortable at all. Okay, so we may have noticed in the last previous problems that there was only one small difference, and that was the number of standard deviations we went from the center to obtain a certain level of certainty. And that number of standard deviations is what we refer to as the critical value, or Z star. So Z star equals number of standard deviations from the mean. Okay, so for example, what is the approximate critical value Z star if the level of certainty is 68%? And what is the approximate Z star if the level of certainty is 95%? So for 68%, we just saw that's going to be happening when we are going within one standard deviation of the mean. So that's going to be a Z star is approximately equal to 1. And for 95%, that happens when we are going out by 2 standard deviations from the mean. So Z star will be approximately equal to 2. Okay, now we're going to call that equal to C, and that will be equal to the level of certainty, or in other words, this is going to be our level of confidence. And usually that's the way we'll be referencing it here, but it's also a level of certainty. All right, so the above critical values are approximate, just like the 68, 95, 99.7 rule itself. And the actual critical value for a 95% level of certainty, which we're going to refer to most often, is going to be 1.96, not 2. So when we have a 95% confidence, that will coincide with a critical value, or Z star, equal to 1.96. And there's a few of these that are just kind of known and we'll use repeatedly in the class. Other ones you're going to need to come up with what that Z star or critical value is going to be. Okay, so in general, it looks like we can create an interval that tells us what to expect for our sample p hat based off the population value p. However, this is the complete opposite of what we actually want, right? We're taking a single sample. We want to be able to say something about the population, not the other way around. So let's consider the following. Michael lives within 3 miles of Kara. Does Kara live within 3 miles of Michael? Well, yeah, that's just distance, right? They are 3 miles apart. So yes, absolutely. We expect p hat, our sample proportion, to be within 3 standard deviations of p with 99.7% confidence. Do we expect p to be within 3 standard deviations of p hat? Again, this is just a distance question. So yeah, same way as we would be expecting Kara and Michael to consistently be the same distance from one another. Okay, so that will be. We can switch P and P hat in distance sentences without causing any major issues. Therefore, since our interval of P plus or minus that Z star or critical value, and that is being multiplied by this quantity here. Remember, that's just the standard deviation. So that means if we add or subtract a certain number of standard deviations from the population proportion, that gave us an interval that told us what to expect for our sample proportion p hat based off of the population proportion. So we should be able to just go ahead and switch the p and p hat to create an interval that'll tell us what to expect for our population proportion based off our sample proportion p hat. And that is what is called a confidence interval. So the confidence interval is given by p hat to start with. So again, I'll go back up. We're just switching our p's and p hats basically. And we're going to go above and below by a certain number of standard deviations. And what we're going to do here, though, remember, is we're switching p's and p hats. So now this calculation will become p hat q hat over n, right, instead of the pq over n. Now, just to remind ourselves, this is our sample proportion. This is our critical value. Critical value, which again was equal to the number of standard deviations. And then this quantity here, this is basically a standard deviation, but since it is being approximated using the p hat instead of calculating it with p, it's going to get a different name. So this is like the standard deviation, but an approximation based on the sample proportion. And just as a little preview, we're going to call this the standard error and label it SE of p hat instead of calling it the standard deviation. Now, what that plus minus means, we're going to add and subtract the quantity z star times the standard deviation from p hat. So our interval itself is actually going to be like a mathematical interval, right? So we're going from smaller to larger, indicating a range on a number line. And that's going to be p hat minus z star times the standard we won't call that quite yet. Let's put it in its full form, times p hat q hat over n. And we're going to go up to as an upper bound, p hat plus z star square root of p hat q hat over n. And so that's our interval itself. Okay, and so what this is going to give us is something pretty cool. This is where we expect the population to lie given a particular sample statistic. Okay, so this is going to give us the interval that we expect P to be in based off the sample proportion P hat. And our assumptions to be able to construct this interval, not surprisingly, are exactly the same as they were before. We still need to have a random sample being selected. We still need to have independence or pseudo-independence. And we still need to have a large enough n based off of our calculation of the expected number of successes and the expected number of failures, right? So those both need to be at least 10. Okay, so using a random sample, an employee at the PCC bookstore finds that 97 out of 112 customers use their credit card to pay for books. And we want to create a 95% confidence interval for what should the proportion be for all PCC students. Okay, so let's put together the information that we have here for what that shouldn't be there. There we go. That'll make it sound better. So our level of confidence, C, is 95%. That tells us what Z star, or our critical value, is going to need to be. For 95%, that Z star is going to be equal to 1.96. We're also told that we have 97 out of 112 customers using the credit card to pay. That is a sample, so that is a P hat. That's going to be equal to 97 out of 112, again, a proportion. So we want to go to 4 decimal places, and that's going to be 0.661. So there's our sample proportion. Now remember, the confidence interval itself, that was given by a p hat plus minus Z star times the square root of P hat Q hat over N, otherwise known as the standard error, or our approximation for the standard deviation. So we can go ahead and perform that calculation ahead of time, and that makes it a little easier to put this all together. So the standard error of P hat, that's going to be the square root of P hat Q hat over N, which with our values is going to be 0.8661. Now, what you can do is you can do the full calculation of that difference, or in your calculator, you can recognize that this is just 1 minus 0.8661. And then divide by your sample size, which is 112. And this standard error, just like standard deviation, is a proportion. So we're going to take it to 4 decimal places, 0.0 0.0322. So that's the size of our standard deviation as an approximation. And so now we're going to go out by 1.96 of those to find the bounds for where we expect the true population proportion to lie. All right, so our sample proportion is 0.8661. We're going to plus minus our z star, which is 1.96, times our formula for the standard error, which gave us 0.0322. So 0.8661 plus minus. Perform that calculation. That's going to give us 0.0631. And that value there is what we refer to as the margin of error. So that's the amount we add and subtract from our sample proportion to give the bounds of the interval. So it's this whole quantity in here, which is equal to the margin of error. So a lot of times you'll see our intervals as given by just p hat plus minus the margin of error to be the bounds. Okay, so now we can go ahead and calculate those. So 0.8661 minus 0.0631, that's going to give us 0.8030, and then add, which will give us 0.9292 as our interval. And again, this is coming from 0.8661 minus 0.0631, and this one is coming from 0.8661 plus 0.0631. All right, and then our last step in these processes, so that's our interval. Now we need to say something about it, like what does that tell us? So there is a template, so a way of writing this where you're not going to get yourself into trouble. And we're going to just practice repeating it in this way. Then once you get a little better, you can perhaps start to finesse it, but it is an interpretation that is often done incorrectly, even in reputable journals. So you want to be very careful with any of the language liberties that you might want to try and take. So our template is we are however much percent confident. In this case, we're 95% confident. 95% confident that in this case, we're talking about proportions. So the population proportion that is going to lie in that interval. So our confidence intervals are always about parameters, okay, and where we expect them to lie. So we are 95% confident that the true proportion of PCC students who use a credit card to pay for books lies between 0.8030 and 0.9292. Now, with our interval, this will come up occasionally, just like it did for, say, our upper and lower fences when we were checking for outliers. It may be that your bounds for your interval will go beyond the range of 0 to 100%, right? So you may have in adding gone over 1, or in the process of subtracting gone below 0. Still make your interval to those negatives or non-reasonable values. And then in your interpretation, that's where you can kind of scale it back to context appropriate values. All right, so next one, let's create a 95% confidence interval for the true proportion of PCC students who own a TI-89 if 15 out of 60 sampled students own a TI-89. So again, we're just running through this process. We want to gather the information from the problem. So our level of confidence is 95%, which means we're going to have a Z star equal to 1.96. We also have our sample proportion, which was given by 15 out of 60 students, or 0.25, 25%. Calculate your standard error, so the size of your estimated standard deviation based on that sample proportion, so 0.25 times 0.75 divided by our sample size of 60. That's going to give us 0.0559. Then we can go ahead and find the interval itself, which is going to be p hat, remember, plus minus z star times the standard error of p hat. And that portion right there that comes after the plus minus, that was our margin of error. All right, so now we can plug in our values. So 0.25 plus minus z star is 1.96, standard error 0.0559, and then 0.25 plus minus, complete that calculation, 0.1096. So that there is going to be our margin of error. Margin of error, how much we're going to add and subtract from our sample proportion. We're going to create the interval itself. So 0.25 minus 0.1096, that's going to give us 0.1382. And then we add to get 0.3618. So there's our interval. Our interval, again, is going to give us a best guess for where the true parameter lies based on that single sample. So we are 95% confident that the true proportion of PCC students who own a TI 89 lies between 0.1382 and 0.3618. All right, and so that's the basic summary of it. The computations of this are probably one of the easiest ones for folks in the class. It's not that hard. It's just the interpretation and appreciating kind of the limitations of what we're saying as well. Okay, so quick word of warning, as we increase our confidence level, the interval is going to get larger. That is, we have to guess more values in order to be more likely to guess the correct value. So we may end up being more confident, but we're going to have less precision, and that is kind of the trade-off. So if we wanted to instead say have, let's go with 10% confidence, versus 100% confidence. We want to be 100% confident that our true population proportion is going to lie in our interval. Well, that's basically going to go from 0 to 1, right? We're going to be filling that whole range. 0 to 1, I guess those would go there, right? Alternatively, if we only needed to be 10% confident, then that means that we can afford to have a much smaller interval instead, because what these statements really are talking about, so both of these are meaning the percent of intervals constructed in this way that will capture the population parameter. So when we say 10% confident, then that means those particular intervals, we only expect 10% of them to overlap with the true population parameter. When we say 100% confident, we expect 100% of our intervals to overlap with the true population parameter. So we need to make the intervals larger in order to ensure that that higher percentage of intervals does in fact overlap with our true population parameter. Okay, so in general, our confidence interval is going to look like a guess plus or minus some wiggle room, and we want to hone up that language. We've already talked about that a little bit. So we define the wiggle room of an interval to be the margin of error, or MO. That's what I'll refer to it most of the time. It is the amount that we are adding and subtracting when creating an interval, and it's given by that portion of the formula that comes after the plus minus. So our z star or critical value times square root of p hat q hat over n, or our standard error. So we can kind of clean that one up. So this is our standard error of p hat. Okay, so that portion there, and this is our critical value. critical value. And the critical value will depend on our level of confidence. That will change it up. And then our standard error is going to be dependent on what we get for our sample proportion. Okay, so let's calculate the margin of error if p hat equals 0.42, and we're going with a 95% confidence level, and we're missing one piece of information that we need to add in here. And let's start with n is equal to 350. Okay, so we're going to start with that one. Then our level of confidence C is 95%, which makes Z star equal to 1.96. Our P hat is going to be 0.42. So our standard error of P hat, that's going to be equal to 0.42 times 1 minus that, so 0.58. And we're going to divide that by our sample size. We're going to assume 350 in this case, and that comes out to 0.0264. So then our margin of error is going to be equal to 1.96 times 0.0264, or 0.0517. So our wiggle room is plus or minus about 5%. Now, how about if we switch this up and instead look at n equal to a sample size of 50, so a smaller sample size. Everything else held the same. So then we would have our standard error of p hat would be the square root of still 0.42, still 0.58, but what we're changing up now is the division by 50. Now note that as you make values larger in your denominator, it makes the overall quantity smaller. So we should anticipate that we're going to have a larger standard error when we have a smaller sample size. And this is true. So we'll have 0.0698 as our standard error, and that's going to make our margin of error equal to 1.96 times 0.0698, which comes out to 0.1368 altogether. So almost a 14% wiggle room around our sample proportion. So this is another piece that you want to kind of recognize, is that as you increase your level of confidence, you're going to increase the width of your interval. And if you increase the size of the sample, then you're going to decrease the size of your interval, because the margin of error does define how wide your interval is, right? So we're going to take a certain number of them, but it's going to depend then on the size of your standard deviation or your margin of error. Okay. So that is that guy. A recent poll shows that 70% of Portlanders like the Trailblazers with a margin of error of 5% when a 95% confidence level was used. And we want to explain what this means. Okay, so let's take a look at what this looks like in terms of the picture. So the poll, that 70%, remember, is going to be a statistic. That's going to be our p hat. So 0.7, that is our what we call point estimate. And it is the sample proportion p hat. Then we have a margin of error of 5%. So that means we're going to add and subtract 5% from it in order to get to our end balance. So this will be minus 0.05. So that'll give us an interval of 0.65 to 0.75 for where we expect the true population proportion to lie. So we expect the true proportion of Portlanders who like the Trailblazers to lie between 0.65 and 0.75. Okay, now is that absolutely certain to be true? No, and that's one thing we want to be really cautious about, is that we're basing this sample proportion on an understanding of the distribution of sample proportions in general. So provided we get a sample proportion that's kind of within those two standard deviations of the population proportion to begin with, then this interval will actually overlap. But if we happen to get a p hat that's over here, right, when you make that interval, it won't overlap with the true population proportion. So in truth, when we talk about this interval, we have a certain level of confidence that we're going to have our true population proportion in there, but it might not. And the probability that the true population proportion lies in that interval is either 0 or 1. Those are our only two options. We can't calculate a likelihood like you might want to. And that's one of the places where there are the most misconceptions and poor statements around margin of error and levels of confidence. Okay, so next question that we can get on this is how many individuals participated in the previous poll? Okay, so how do we get around to that? Well, the N is associated with the margin of error. So that's the place that we're most concerned about. So we still know that we have our level of confidence is going to be 95%, which means our Z star we know is 1.96. We know that our P hat is equal to 0.7. And we know that our margin of error is 0.05. What we don't know is N. So the place, again, where N shows up is in margin of error. So let's start with our margin of error formula. And that's going to be Z star times the standard error of P hat. Right? And so otherwise, we can write that out longer hand, which is the square root of P hat Q hat over N. All right, so now we can fill in everything that we do know. And we do know the margin of error was 0.05. And we do know that Z star was equal to 1.96. And we know that P hat was 0.7, so Q hat must be 0.3, and what we don't know is N. So the process I'm going to describe here is one that I'd like you to use regularly for this class. Now, there are other ways of doing this, absolutely, but it is easier in our case to kind of keep track of the numbers and not lose accuracy by waiting till the very end to do the calculation part. So what we should recognize is that the N is trapped under the square root. So we're going to need to release from the square root. And we do that, we undo square roots by squaring. So we're going to start by squaring every value in here. And then we'll square this big guy. Now, squaring the square root undoes this, but does not actually square the numbers themselves. So I'm going to rewrite this now a little bit more cleanly. So I have 0.05, that's squared, 1.96, that's squared. Then I have the 0.7 and the 0.3. Those are not squared and still in the numerator. And then I have N in the denominator. So I've just kind of cleaned that all up together. Now I can get N by itself by multiplying both sides of the equation by N, dividing both sides of the equation by 0.05 squared, or in other words, switchy doodle the N with the margin of error squared. So then N will be equal to 1.96 squared times 0.7 times 0.3 divided by 0.05 squared. And it's at this point that you want to go ahead and perform the calculation. And in my calculator, I'm getting 322.7. Now, this is not reasonable for a sample size. We need a whole number for sample sizes. So you always want to calculate to a decimal, okay, up here. So leave as a decimal, and it can just be to 1 or 2 places. That's more than adequate. And then you're going to take that and round up always to the next whole number. This is the same sort of process as finding the minimum sample size. We're going to do a calculation to a decimal. Know that we must have a whole number. So if that result is not already a whole number, round up regardless of the decimal value to the next whole number. So the sample size in this case was 323 is what it would need to be for that one. Okay. All right. So let's take a look at another example. So a pilot study found that 25% of students have used the Student Learning Center. So a pilot study are things that we do as a preliminary kind of quick look at what's going on to basically kind of get our foot in the door and to see if the results warrant going deeper and looking at a bigger study that'll end up costing or take more time. So we've got a pilot study found that 25% of students have used the Student Learning Center. If we would like to determine the true proportion of all PCC students that have used the Student Learning Center to within 1% and with 95% confidence, how many students need to be sampled? Okay, so in this case, we're looking for N. We want to know how many students were sampled or need to be sampled to reach these desired criteria. So we have our level of confidence is 95%. So that means Z star is going to be 1.96. We know that right away. We also know that our margin of error is going to be 0.01 because we want to be within 1%. So that within value is the margin of error. It's our wiggle room, right? Then we also have our p hat. In this case, it was given to us. We're going to use the pilot study result as our best guess in the moment for what the p hat's going to be. So we'll take that. Now, if we were not given any preliminary information, we don't have anything to go off of, then we use the worst case scenario for p hat and make it equal to 0.5. So let's just make note of that. If no previous information, study information is given or available, use p hat equals 0.5 as the worst case scenario. Okay, so the larger our p hat, okay, but we need to balance it, right? Because then we make a really small q hat if we get too small. But when we have the largest possible values in product with one another, that's when we're going to have the biggest numerator, which means we'll get the biggest sample size necessary. Now, it could have been that we could have worked it out for lower, but at least this way we're going to be certain to reach our goal of that 1% wiggle room or margin of error. All right, so then we're going to set up our margin of error formula because, again, that's where the sample size comes in. So margin of error is equal to Z star times the square root of our p hat, which is 0.25 because we were given some previous information to work from, q hat over our unknown N. Next step, square all of those parts of the product. Square undoes the square root. Rewrite it more cleanly. Equals 1.96 squared times 0.25 times 0.75 divided by N. Switch the N and the squared margin of error. 1.96 squared, 0.25, 0.75 divided by 0.01 squared. Then put it into your calculator, and I get 7203. That ended with a whole number, so that is our sample size that we would need. So we would need a sample of 7,203 students. Okay, and then that would ensure that we have a margin of error of no more than 0.01. So we'll get our wiggle room to within 1%. Okay, so some more terminology. I've been using it a little bit, but the point estimate, that is a way of talking about the center of the model, which in our case is p hat. We do confidence intervals around means and other values or other statistics as well. In our case, in our class, we're just using p's and p hats though. The standard error, we saw this before. That is our guess for the standard deviation based on the sample. That's just where we've switched P's with P hats and run through the calculation in the same way. So Shauna surveyed 120 people at Rose City Comic Con and found that 50 thought that the Flash was the best superhero. What is the point estimate for the proportion of all people who think the Flash is the best superhero? And what would the standard error be? And what would the margin of error be if she wants to be 95% confident? And what is the confidence interval? All right, so we have a few different things to run through. our point estimate, that is p hat. Okay, so that will be the 50 out of 120 people that were surveyed, or 0.41667. Then our standard error, that is just the calculation of standard deviation, but exchanging p hats for p. So this will be 0.4167 times 1 minus 0.4167, and that's divided by our sample size of 120. So the standard error is 0.0450. Margin of error, our wiggle room then, is going to be equal to our z star, which is 1.96, since we're dealing with 95% confidence. And that is times our standard error, 0.0450. And so our margin of error is 0.0882. So our wiggle room around our point estimate is about 9%. So we're looking at expecting our true population proportion to be around that 42%, give or take the 9%. So our confidence interval itself, more formally, is going to be that 0.4167 plus minus 0.0882. So minusing, we'll get 0.3285, adding 0.5049. Now, please note that with our confidence intervals, again, they're mathematical. They are representing a range on a number line, always going from smaller to larger. All right, so then we are, again, following the template, 95% confident that the true, there's U in there, proportion of people who think the Flash is the best superhero. Hero lies between 0.3285, and 0.5049. Okay, and so that's basically all of those put together. So we've got our margin of error that's added and subtracted from our point estimate to give us the confidence interval, which is where we are expecting the true population proportion to lie. But we know it may or may not. This is just our best guess based on our assumption about the distribution of sample proportions. All right, so just a couple last things, but what if we let our level of confidence be something other than 95%? So we want to be able to do this in general, and our general process is to place the level of confidence in the middle of a normal model. Then we're going to find the area left in both tails. Then we're going to determine the area just in the left tail, use GeoGebra to find the z-score boundary, and we're going to switch that to a positive. Okay, so let's run through those steps and what you'll need to present. Okay, so we're going to need to make our picture first. Okay, and then we want to show in the middle of our model where our level of confidence lies. So this is our level of confidence. And since that is 90%, then that means that leftover in both tails is going to be 10%. So we'll take 100% minus the 90%. That means we have 10% in the two tails. Now we only want the one left-hand edge because we're just going to go with conventions of looking at that one region, always thinking about the percentiles, right? So this 1/2 of the 10% will be 5%. So right there is 0.05. Now we're going to want to find the bound in terms of the z-score. Now doing that just means we're going to do the same as our inverse normal operations, but we're going to do that with the 0 and 1 for our parameters in GeoGebra, since what we care about, right, is going to be a z-score this time around. So in the GeoGebra program, let's see if we can get that. over here. So we have 0 and 1 is our bounds here, and we want to go less than, and we are going to want to give the area. So remember the amount after the equals, and that is going to be 0.05. There we go. There's our 5%. Enter. And then we have negative 1.6449. If we were looking at this just in our way of doing it, right, we would say this is negative to 2 decimal places, 1.64. And so then Z star would be equal to the absolute value of that, or just the positive version of it. So 1.64 would be our Z star. Now, this is a common level of confidence. So while we would do this calculation, if I was asked to show you what it is, we will actually be given some of the common levels of confidence. So this is a common level of confidence. And as we saw, the value, it was negative 1.6445 or something. The rounding was at kind of the edge of where we would do it, right? And so when that happens, for the more formal versions of these Z stars, they'll go to 3 decimal places to account for the fact that to round or to keep it down or to round it up is kind of borderline why we would be doing that. So since this is the common level of confidence, you will use 1.645 to be Z star, because they're going to just keep that 3rd decimal place for rounding issues. So when it's one of these common ones, use the listed values. You'll see this on your formula sheet. It's in the notes in D2L as well. And so you'll want to use those common ones. But this is the process for finding it. Now, 85%, this is not a common one. So the only way you'd be able to find the Z star is to go through this calculation. And so in this one, again, always start with drawing that picture to show what we're looking at. The middle region, this is going to be our level of confidence. So this is where we have 85%. That's our level of confidence. That means the 2 tails together, that's going to be 100 minus 85%. So that'll be 15% in the 2 tails. We only want the one to the left. So this one will be half of 15%, or 0.075, so 7.5%. And then that will allow us in GeoGebra to get Z, which will be a negative value. So let's take a look at that again. Okay, so we're still doing less than, but now our area is going to be 0.75, enter. And so we get negative 1.4395. So we can be pretty confident with saying that's negative 1.44 with rounding, and Z star would be positive 1.44 because we're not needing to sign it. We're just saying the number of standard deviations we're going to want to go above and below. All right, so that's how we go about finding Z stars for other levels of confidence. And then let's take that to one more step here. So Skittles claims that 20% of their candies are grape flavored. We think the actual proportion might be less. And so to test the claim, we want to test the claim using a hypothesis test. If we use 15 grape candies out of 100 candies tested, and we're going to assume a 10% level of significance. All right, so we're going to run through a hypothesis test first with this. So H naught, HA colon proportion claimed by the company is what we're going to assume. And then we think the proportion is less, so less than 0.2, where P is the proportion of grape flavored Skittles. Okay, then we need to have our P hat. That is going to be based on our sample, so 15 grape out of 100, so 0.15. Then we're going to calculate our standard deviation for our And our expected value of p hat for our model, we'll just assume we've met the condition. So this will be 0.2 times 0.8 divided by our sample size of 100. So our standard deviation, not standard error this time, is 0.0400. So that's going to give us our model, which is going to be normal, 0.2, 0.0400, proportion of grape Skittles. Whoops, there it is. And n equals 100. So there's 0.2. And then our result was 0.15. And we shade in the direction of our alternative hypothesis. So we're going to shade less than. Then we need our z-score. So 0.15 minus 0.2 divided by 0.04. And so our z-score is negative 1.25. This is not unusual. So we are going to be expecting to fail to reject the null hypothesis. We don't have a result that is unusual or unlikely enough for us to question the 0.2 as the population proportion. So probability of p hat being less than or equal to 0.15 is equal to the probability that z is less than or equal to negative 1.25. Using GeoGebra with that z-score of negative 1.25, it's 0.1056, and that means our p-value is equal to 0.1056. So yes, we are going to fail to reject. So given p-value of 0.1056, which is greater than 0.05, this case 0.01, or sorry, 10, that's our level of significance. We are going to fail to reject the null hypothesis. We fail to reject the null hypothesis. Okay, so now we're going to follow up. Now we've rejected the null hypothesis. So what should we actually assume to be the true population proportion? And that's where the confidence interval comes into play. So we're going to follow up with a 90% confidence interval. So we have p hat, and that is equal to the 0.15 that we got from our sample. Now, the big switch here to doing a confidence interval is we're no longer assuming p was equal to 0.2. Instead, we're using our sample result for our approximation of the standard deviation. So we're finding standard error now based on that 0.1585 divided by our sample size of 100. So our standard error, 0.0357. We are doing a 90% confidence interval. That is, again, a standard one, so we don't have to run through the calculation of our z-star. We can just use the fact that z-star is going to be 1.645 for a 90% level of confidence. So then the interval, 0.15 plus minus 1.645, our z-star, times our standard error, 0.357, and then 0.15 plus minus our margin of error is 0.0587 altogether. And then we subtract to get our lower bound of 0.0913, and our upper bound is 0.2087. So we're going to write our interpretation of this so that we are 90% confident that the true proportion of grape Skittles lies between 0.0913 and 0.2087. Now, notice what is in the interval. Well, what is contained in the interval is actually our p naught, our null parameter. So null parameter of 0.20 is in the interval. Okay, so that means it is one of our potential candidates for the true population proportion, which is why we did not reject it. Okay, so when we compare the two processes, our hypothesis test and our confidence interval, they kind of give us very similar information. When we have our confidence interval, those are the null parameters that we would kind of accept as um, viable options for a true population proportion. When we have null parameters outside of the interval, that's when we're going to reject them because they're not ones that we would predict to be likely candidates for the true population proportion. So that's kind of the cool connection between them that we're going to look at a little bit more in the next video, since it's, gets a bit long as it is. But here is another quick example to go over. This is one of the easiest, hardest questions for stats, actually, in general. So suppose someone creates a 95% confidence interval and it is from 0.2 to 0.25. What is the point estimate? And what is the margin of error? And then what is the sample size and number of successes? So we have a few different things that we're going to want to test out here. So the first thing is think about how we form that interval to start with. So remember, we start with our point estimate of p hat, and then we're going to add and subtract the margin of error from it. So that gives us an interval altogether that is 2 margin of errors wide. All right, so the distance from 0.25 to 0.2, that 0.05 is a width of 2 margins of error. So the margin of error is going to be 1/2 of the difference between 0.25 and 0.20. So 1/2 of the width of the interval is what we're looking for. So our margin of error is going to be the 0.05 divided by 2, which is going to be 0.025. That's our margin of error. Now, the other thing we can look at is, okay, well, the p hat lies in the middle of it, and we are moving one margin of error to the middle and then another one margin of error to get to the end of the interval. So one way to get to the point estimate, p hat, is to know that we're going to have to start at our one end, and then if we add a margin of error, we're going to land at the point estimate. So 0.225 is going to be p hat. Now, we could have also taken it from the other end and walked back, or you could have done the midpoint of the interval. Any one of those methods should get you to the same place. And technically, you don't even have to show me any work with this. Once you get in the hang of it, you're going to be able to figure those ones out pretty quick. But it takes a little bit of recognition of the process moving forward to see how you would undo it. Now, this is similar here for finding the sample size and number of successes. So we have a 95% confidence level. So we know that Z star is going to be equal to 1.96. We have our p hat, we just decided was 0.225, and we have our margin of error that is equal to 0.025. Now, the number of successes, that's going to be coming from a p hat calculation, right? So that's x over n. So provided we know what n is, we can go ahead then and fill in the rest of those values to calculate x. So we need to get n first. And remember, n shows up in our margin of error formula. So let's go ahead and jot that down. So that's the p hat, our margin of error, 0.025. That's going to be equal to Z star 1.96 times the square root 0.225, 0.775 is Q, and divided by N, which is unknown. We're going to then square everything. Okay, and then that will be able to simplify to 0.025 squared equals 1.96 squared, 0.225 for P hat, 0.775 for Q hat, divided by n. Rearrange the formula. So then n is equal to 1.96 squared, 0.225, 0.775 divided by 0.025. There we go. And all squared. And so that's going to give us a result of 1071.8, which means the sample size was 1072. Now, knowing that, we can go back and find our number of successes. So that's 0.225 for p hat. Put that in. And then x is our unknown. We know we had a sample size of 1072. So multiply those two to get to x, 0.225 times 1072. That'll be x. And so x was 241.2. Or we can just round that back down to 241 is likely our number of successes. So number of successes in our sample. Okay, and so that covers it. Just to double check where we were at. That covers what we've got for confidence intervals, and we will come back to take a look at the combination of them more closely.